Thing's creepy. Welcome back, folks. Talking about transients and charging and discharging capacitors and inductors. The last 4 videos have all worked through developing the form of the first order response. So we have a circuit that has either a single inductor or a single capacitor, and the response is going to look similar, but it might not look that way at first glance. Maybe you've caught it while I was going through those videos, but I want to put them all on the screen now, and I want to look at what happens to all of these responses as time progresses. Okay, so let's get rid of that guy. I don't trust him. And look at this. These are the 4 forms that we developed in the last 4 videos. So we have the discharging capacitor, charging capacitor, discharging inductor, charging inductor, and I'm telling you, we can make these all into a general form that fits all 4 of these. It's a little jumbled right now, but we can do it, and it's important. And we're going to use it in the coming videos where we actually use this to analyze transient circuits. Okay, since it can either be a voltage or a current, I'm just going to call it X. Okay, and we'll make it a lowercase x. I put the little tail on my x's too. Okay, and it's a function of time, so it's either a voltage or a current, but it takes on this form. Each one of these 4 equations can be rewritten as K1, so it's some constant K, we're just calling it K1, plus K2 e to the negative t over tau. Okay, then we just have to figure out what K1, K2, and tau is for each of our circuits. And that's what we're going to do here. So if we look at this voltage, the discharging capacitor, there's got to be some constant term by itself. And there is, even though it doesn't look like there is. Okay, we say that this is K1 equal to 0. Okay, K2 in this case is equal to Vc of 0, and tau is equal to Rc. It's really that simple. Okay, so if we come down here, we can take that same approach. We can say, well, what lines up in our charging capacitor to this form? And we can say that for the charging capacitor, K1, now we have a constant term. K1 is equal to Vs, K2 is equal to our initial condition minus Vs, and tau, once again, is equal to Rc. Okay. Rinse and repeat from there. Okay, over here we have K1 is equal to 0, K2 is equal to IL at 0, so there's our initial condition. And why did I write Rc? That's what I get for wanting to copy it over. That's L over R. Glad we caught that. Okay, so tau in this case is going to be L over R. That's one of the reasons I kept them together, because I want some value of tau. I want a constant in the denominator, and that's going to tell us something about the response. Okay, last one, K1 in this case is Vs over R. K2 is our initial condition for the current minus Vs over R. And once again, looking at that denominator, tau is equal to L over R. Okay, so all 4 of those solutions, even though they're a little different, can fit into the format of K1 plus K2 times e to the negative t over tau. And that's another one that ends up having a little bit of rhythm to me because I'm going to repeat it a lot. K1 plus K2 times e to the negative t over tau. And then we just have 3 pieces of information we need to figure out for each circuit. Now K1 and K2 tell us where the circuit is charging from and where it is charging to. Okay, so that has to deal with either the capacitor voltage or the inductor current. What I want to look at is tau, and tau is rather interesting. We call it the time constant. Okay, and let's highlight that. We call that one the time constant. That's going to tell me how fast this circuit is transitioning between the two steady states. So K1 and K2 help me figure out what those steady states are. Tau tells me how quickly it's moving between those two steady states. So in order to do that, I made a little circuit and I made the numbers as simple as I could. 1 volt, 1 ohm, 1 farad, and we're even going to say that VC of 0, so the voltage across the capacitor, at our initial time 0 is equal to, not 1 volt, that'd be boring, is equal to 0 volts. Okay, so if we want to write out the expression for this, we can, we can go the long way, or we can come back up here. So Vs, right, Vc of t, is this going to be behind my head? It's going to be behind my head. And I want that form there. Hold on, bye-bye. Okay, so Vs in this case is 1 volt, so let's just call that 1, plus Vc of 0, which in our case is 0, minus Vs, ooh, that's going to make this one a minus, okay, minus 1 e to the negative t over tau. Tau is R times C in this case. Okay, so I have 1 ohm times 1 farad, so that's going to be 1, it ends up being 1 second. Okay, so hey, I'm back. Now we can scroll up a little. That's our expression for the voltage across that capacitor. Now, ooh, I gave something a little way over here. The thing that's changing with time, this term's a constant. That's not going to change. This one is, and it's going to change according to e to the negative t over tau, which is 1 second in this case. And as that changes, we can look at what happens at 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, so on and so forth. So what we're interested in is when the change starts to slow down. So at 0 seconds, we're at 100%, or 1 times whatever that initial condition is. Between 0 and 1 second, look, we've dropped 63 and change percent of our of that transient. Okay, so within the first second, we're changing a lot. But then it starts to slow down. We go from 36 down to 13, so we're around 13% change in that next second. And then we're like right at 5, right? So we've lost about 8% of our charge there. From 3 to 4, it looks like we've lost about 3%. From 4 to 5, we've lost about 1.2%. Okay, at 5, we have this habit of saying, hey, it's good enough. We started up here at 100%. At 5 tau, let's do it over here, since I'll have more room to write. We say we're within 1% of the transient. Change in value. Okay, so 5 tau is something that we kind of by convention use to say, hey, we're done with the transient. That's how long it's taken. So all of that comes from R times C for a RC circuit, and it comes from L over R for an RL circuit. If we're charging it, something similar happens. Okay, so look over here. We start at 0% of the change, and within that first second, we gain 63%, and we kind of go on and progress, and look what happens at 5. Again, we're within 1% of the change. So whether you're charging or discharging, that natural logarithm, it's not a natural logarithm, that natural exponent is what controls how quickly it's happening, and specifically the denominator, okay, tau there, changes how quickly it's moving. Okay, so I have a MATLAB script. Plots help a lot as well. So let me grab a MATLAB script and let's plot this one out and let's see what happens to it. Okay. All right, so here's our plot. I don't have, well, I can label them now, right? So let's grab this. This is our voltage for our capacitor. One of them's charging, one of them's discharging. I'm hoping you can figure out which is which, right? So let's plop this down here. And let's say that this is our charging cap. And our discharging cap. I'm going to write it over. I'm going to write it down here. Discharging. Oh, behind me. Great. And beneath the screen. Good, good, good. Discharging cap. Okay. That's what they are. Look at all that change in the first second. Okay, so we go up 63%, we go down 63% in that first second, and then it starts to asymptotically approach its final condition, okay, whatever it's going to be in the next steady state. It looks like I made this 10 volts. It's horrible. Oh, you know what we do for that? You know what we do for that? We change the example. I can get away with that, right? Okay, so it would look something like this. Okay, and then this is e to the negative t over tau for this column over here, e to the negative t over tau. Nope, that's not true. Oop, that's 1 minus that. Okay. And that tells us how much it's going to change. Now, if I change the values of R or C, it's going to change how long it takes. So if I make either of those values larger, if I either need more charge to flow, it's going to take more time. Or if I make it harder for that charge to flow, it's going to take more time. So R times C is going to be larger, and rather than taking 5 seconds, okay, this is where we have our imaginary cutoff, where we're within 1% of the change, 5 tau. Instead of taking 5 seconds, it's going to take much longer. Okay, so let me see if I have enough room here. So, and let's change things up. So if we say R is equal to 10 ohms, and C is equal to 10 farads. That's huge. Not something you're going to find in your consumer electronics kit. That's pretty big capacitor. And let's alter the MATLAB script. I got it over here on my other screen, and I should be able to just drop in some constants there. And we get a very similar looking plot. The shape is the same. But look at that horizontal axis. Okay, now we're talking about 100 seconds, 200 seconds, 300 seconds, 400 seconds, 500 seconds. A good long time for these voltages to respond. Okay, but at 5 tau. Okay, well, what's tau in this case? Tau is equal to R times C, and that is going to be 10 times 10, so it's going to be 100 seconds. That's our time constant. This is 1 tau, 2 tau, 3 tau, 4 tau, and here we have 5 tau. Okay, we reach 5 tau. We're within 1% of the change up here. And if we're discharging, same thing. We're within 1% of the change down there. That's it. So the time constant controls how quickly we move between transients. That, coupled with K1 plus K2 times e to the negative t over tau, we're going to use that, and we're going to analyze transient circuits, first order transient circuits. That's what we limit ourselves to for this semester. All of these circuits might feel simplistic, but take another look at this. take another look at this. Last thing. What's that? Okay, that's an equivalent circuit. That is a Thevenin equivalent circuit. So if we have a single component and we need to know some of these values, we get to Thevenize around it. And we get to simplify it down to one of these forms. Okay, so this is a Thevenin equivalent circuit. Voltage supply with a series resistance or impedance, depending on the type of problem. Okay, I want to analyze some circuits, because that's what we're here to do. Let's go analyze some circuits, and in doing that, we're going to figure out how to handle switches. Okay, electromechanical components, yes, but they can cause transients. What happens when I turn the power on? What happens when I flip a switch that is a user input to a microcontroller? How does this circuit respond? That's what we're headed to next. Stay tuned and good luck.